So now Max, not only can it understand you, but it has legs to go search the database. It has the brain to go understand and analyze the insights, and then it's got the voice to give it back. Since day one, really, AI and specifically natural language have been at the heart of what we were trying to bring about. And the reason for that is fundamentally the very first computer program was written, almost 200 years ago. But a program, by definition, is a human speaking in computer language. And so the goal, the AnswerRocket goal, was to stop that, to have the computer speak the human language, right? So that was our very initial purpose, and sort of to erase that 200 years of history of people having to speak in computer and instead have the computer learn to speak what we do. So it's been a core aspect of the solution, from the beginning. The idea of a prompt of engaging with text or even with voice, whether it's from mobile or from desktop, basically communicating naturally with the machine and having the machine naturally communicate back to you. That's been kind of the central theme of how we've been seeking to democratize access to data, right? That's the idea, is that the democratization happens because everybody can speak, right? And there's some really good studies out there that talk about, for every person that can read a spreadsheet, there are 10 people that can read a sentence, right? And for every person that can read a sentence, there are 10 people that can read a graph, right? So if we can understand people's natural language and talk back to them in pictures and in words, that solves a problem that's really never been solved before, and that's been our goal. The fundamental technique of AI working using these things called neural networks or neurons, artificial neurons. This has been around since the 50s, the 1950s. So again, nearly 100 years of this concept, and they've been getting larger and better as machines have gotten better and faster. The techniques have improved and so forth. And so this fundamental idea from a long time ago that said, hey, can we make something that's like a human neuron and make a group of those like a human brain? That's really been evolving and evolving and evolving. And so suddenly when a machine starts to act like a human in terms of being able to translate languages and understand concepts or finish stories or whatever, these large language models are really just big groups of those early designs, right, of those early neural networks. Now they're organized in a very special way, right? There have been major advances kind of in layers, things like deep belief networks and autoencoders, things like transformers. These are layers of the technology that have happened along the way. But fundamentally, a large language model is just a really big group of artificial neurons organized in a special way, the same way that our real neurons are organized in a very special way. And they're set up in a way that they can take in what a person is communicating, and they can answer back in that same fashion. A large language model is part of a group of algorithms, a kind of program, right? That's called an autoencoder, right? So I remember the very first one that I worked with was in 2007. It turns out the post office has a giant database of handwritten digits, because the post office needs to be able to read all kinds of crazy envelopes where people have written really sloppy 8s and that look like 3s and really sloppy 4s that look like 9s. So they have tens of thousands of examples curated in a database somewhere. And there's a guy named Jeffrey Hinton, who's out of the University of Toronto. I think he's at Google now. But he took all that data and he fed it into a computer. And this is the brilliant thing about his work, is he didn't tell the computer which ones were 3s and which ones were 8s, which ones are 2s and which ones were 5s, right? He just gave it all to the computer and said, you figure it out. And this computer, sure enough, created 10 separate groupings of these things, and it figured out what 0s and 1s and 2s and 3s and 4s and so forth were in that grouping, right? Using this autoencoding technique. Well, and then the wild thing when I recreated the results of that original paper, and so did everybody else out there in the AI community. When I recreated that, the wildest part about it was not only could it recognize all those previously human-made handwritten digits, but you could ask it for an original too, and it would make an original two. It wouldn't look like a bunch of static, right? It would look like a two that was nowhere in the database, right? So this is kind of a chilling feeling, right? That's called a generative model, right? And that's the G in GPT. The generative model says, hey, after you've shown this thing all the examples of everything that you want to train it on, that you want it to learn, right? Then you can just kind of poke it and say, okay, well, now what do you think? And it'll actually generate back to you something that's like all the stuff you trained it on, right? So before these generative models, AI was all about saying, let me beat a bunch of examples into the machine until it guesses right on the next one, right? And that in sort of adjusting all these really fine-tuned numbers, these generative models all of a sudden can kind of flip that around, right? They can not just be able to look at the inputs from the outside world and say, oh, I think that's a cat or it's a dog, I think it's a 3 or a 5, or I think whatever the conclusion is from that algorithm. But they can, the recommendation for you is to watch the next John Wick movie, right? Those kinds of things suddenly come out of these generative models that are able to basically be kind of poked from the outside and caused to go into motion and caused to do their work. Well, it turns out if you take, back to my handwritten digits examples, if you take a person who, like, for example, I grew up in Spain, we put lines across our sevens, right? Our seven, you draw a normal 7 and then you put a line through it. You do the same thing with Z's, right? Well, that's almost like another variety of language, right? It still knows to put those things with the 7s. It doesn't get confused and put them with the 4s or with the 2s. Well, it turns out when you take a language model and you train it on a whole lot of English, and then you train it on a whole lot of French and a whole lot of Spanish and Hebrew and Chinese, it turns out it's able to learn all those separately. And then, and this is really where these emergent phenomena come from, right? The idea of emergence in AI is unexpected results that come out of the combination of two or more things. So there's an emergent phenomenon, which is that the idea of house in one language and the idea of house in another language are really closely related inside the quote unquote mind of the machine, right? That it determines that those two concepts, house and casa, which is the Spanish word for house, that those two things are really very similar to each other because of the way that they relate to everything else. The English model showed that a person opens the door of a house and dogs live in a dog house and houses have roofs. Well, all those same kinds of ideas exist in Spanish or in Hebrew or in French or in Chinese. And so when the machine is organizing all these thoughts, and let's not get philosophical, but let's call them thoughts. When it's organizing all of those thoughts, it turns out the concepts that it builds in two different languages end up being very similar. And so it's able to translate simply by relating where each of those concepts are within the context of its thoughts, right? Of what it's done with the word. So it's the idea, the idea there. It's not thoughts. It's called embeddings. The idea of embedding is what is the large language model's concept of a word or a phrase or a sentence or a paragraph. The same as if to a human you went up and said, a red fire hydrant was on the corner. Well, your mind has now gone into a certain state. If I put you in an MRI machine, I could scan your mind and it would be a certain state, right? You have that thought in your brain. The embedding is the representation of the thought in the brain of the large language model, right? And it turns out again that I can take the same phrase in two different languages, and your brain would go into the same shape if it understood those two languages. I can give that same phrase in two different languages to a large language model, and it will get a very similar shape as far as how it relates those things ultimately inside of its embedding. So Starbucks, if you say I want a hot drink, they have 3 sizes, right? The 20 is the largest one. If you want a cold drink, they actually have 4 sizes, right? There's an extra large cold one, and you might say, why? Why is there an extra large cold one and not an extra large hot one? And the reason is because the top seller in the hot drinks is the middle size. In other words, they made them bigger and bigger and bigger until sales started going down. They did that for hot, and it turns out they only need 3 sizes. You do that for the cold, it turns out you need 4. You need that 4th size to know that you've reached the peak of the performance. Well, same thing in large language models, right? We've been making bigger and bigger language models, since I was a wee child, right? Because a long time ago in a galaxy far, far away, you would have 2 layers of 30 neurons, and that was worth writing a paper about in a scientific journal, right? Well, now 2 layers of 30 neurons is 1/10 trillionth of the size of the neural network. Not literally, but it's a very, very, very small network. So these networks keep growing bigger and bigger. Now, unlike the Starbucks drinks where they figured out the highest size that's the biggest return, we haven't figured it out yet for language models. We keep making them bigger and they keep getting better. And so the question is, where is the end? The original language model, the way that it's trained, the same way that the post office said, hey, here's a whole bunch of digits, figure it out, right? The way that these language models are trained is, here's a whole bunch of internet stuff, figure it out, right? And literally the figure it out part is, tell me what the next word's going to be. I'm going to give you 1,000 words, tell me what the next word's going to be. And so the language model, on one hand, you could say, yeah, well, I could just have a database, I could save the internet, and then I can tell you what the next word's going to be, because all I got to do is go find the 1,000 words that you gave me, find it on the internet somewhere, and look at the next word, and boom, I've got the answer, right? Now, if you do that, you haven't generalized at all, right? Because now if I change one of those 1,000 words, you're not going to know what the next word in that list is. So language models they're not allowed to memorize that way, right? They're not allowed to, meaning that the program as it's written doesn't allow the language model to simply store away what it's been taught. It has to generalize it. It has to say, oh, you said having, had, 3 different misspellings of that verb. I know that all those are the same thing, right? Or you said something in English and it looks a lot like something that I saw in French, so I'm going to remember that in the same way. I'm not going to remember that exists in English or that it exists in French. I'm simply going to remember the concept of whatever that idea is. And so so basically, this idea of training it to learn what the next thing is how the language model gets really, really smart. And you can imagine if you took every list of 1,000 words on the entire internet and gave it that as an example, then you've got billions of examples to train with, right? And so that's really that super big training set is what allows us to keep building bigger and bigger networks to learn everything that's going on in here. All right, but if all you ever did was learn to say what the very next word is, then you wouldn't really be able to have a lot of chat dialogues, because all that stuff on the internet, the Wikipedia and the article, the laws of the state of Kansas and the case history for the courts of Mexico, whatever it is, all of that, it's not full of a bunch of chats, right? It's not full of a bunch of conversational language. There's some, sure. You can watch interviews. If you transcribe YouTube videos, you're going to get a nice list of chats, right? Of conversational chat. So it could learn some of how to predict the next word, but it's a really bizarre thing to try to teach one of these language models how to chat, because it needs to say something and then wait for you to answer, not try to guess your next word. It needs to let you answer, and then it needs to try to continue what it said before, knowing what you said, right? So it's a very different kind of way of thinking about language. If all you ever learned to do was predict the next word, then you're kind of a know-it-all, right? You're kind of a, you want to just keep talking like I'm doing right now, instead of letting the other person have a conversation. So what the ChatGPT specifically was all about saying, let's actually train it to know when to stop, to know what to say, to know how to listen. Essentially, the reinforcement learning came in as a secondary stage that says, yeah, I know you know how to finish every sentence anybody ever said on the entire internet. You're so smart. Great. Now I don't need you to do that. What I need you to do is actually have a sensible conversation with a human. And so there has to be some reinforcement, just like there would have to be if you had a person who had never had a conversation and suddenly they're out, trying to have a drink at a bar. Well, that wouldn't be much fun to have a drink with, right? So some reinforcement learning goes through the process of getting that person to stop guessing what the next word's going to be and do a little bit of active listening. You can think of it as a kind of a wonderful marriage, right? So AnswerRocket has been in development for a number of years, learning how to understand databases, find insights in data for various different industries, right? For pharma, for banking, for insurance, for packaged goods, for video games, whatever that insight-seeking behavior is that we've been teaching AnswerRocket with a thin layer of natural language understanding around it, and a fairly sophisticated insight selection model, right? So we have become really good at saying, hey, based on the data that you have and the question that you've asked me, here are some things that I can tell you that are really insightful, like an analyst would have provided you. Now, GPT comes along, and well, what it does really well is it understands the question the user might ask, right? So where AnswerRocket might have needed very, very specific timeframes, measures, facts, right, to identify the question, GPT can tell right away, oh, you're trying to compare two things to see if they grew the same, right? Or, what you're after is a deep understanding of where are the anomalies in this list of things, right? So GPT understands that. It doesn't know how to get that answer. It understands what you want to know, but it has no idea how to get it. AnswerRocket is kind of a perfect mate to that, because it can understand what the user wants, connect up with AnswerRocket, and now all of a sudden Max understands you because of how smart GPT is, and it knows how to answer because of how smart AnswerRocket is, right? Now, Max does all the analysis and finds out that, the comparison or the trends or the outliers that you're after. But then the question is, how does Max explain it back to the user? Now, Max normally would give a chart, it would give a list of facts, it would cite a whole bunch of different really interesting things. The great thing about going back through GPT on the way out back to the user is that we can get GPT to explain those facts back to the end customer. So GPT can say, oh, I'm reading good news. I'm telling you something really great. Isn't it wonderful that this has occurred? Max didn't know that. Max didn't know it was good or bad, or sales went up. Sounds like a number, right? To Max, GPT knows that sales going up is a good thing, right? These are logical constructs that exist in language, right? That Max, Max, unless we kind of build that in and hand tune it and tweak it, Max doesn't really have, on its own, doesn't have that capability, or AnswerRocket doesn't have that capability. So now Max, not only can it understand you, but it has legs to go search the database. It has the brain to go understand and analyze the insights, and then it's got the voice to give it all back to the user in a way that makes it really feel like you're collaborating with a coworker, collaborating with an analyst that knows all of your data inside out better than you ever really want to, and is really is going to accelerate your day by taking the bulk out of the analysis time and giving you back the time to consider what the results are, to figure out what you're going to do next. First prediction in a 2-year time frame, GPT will not be the only standout, right? So this technology is unique and special. GPT is, but OpenAI doesn't have a monopoly on it by any sense. So I think there'll be a lot more models that perform as well as or better than GPT. They'll be specialized in different areas. The next part is going to be the movement of the model down into, right now it's in the cloud because that's where you can have really expensive infrastructure and apply it to a lot of different people. In a maybe not a 2-year time frame, but not much longer, it'll be in your phone, right? It'll be something that's rapidly available, widely available to everyone. Not the giant version that's been trained on everything that's ever been written, right? But the small enough version that can make an appointment for you and talk to your friend's chat agent to settle whether or not you're going to have a drink after work, right? Those kinds of things, that'll all be in place, right? Because it's much easier. We've been in a world where getting my phone to talk to your phone is this tedious process of writing API calls and IP addresses and interconnections and making things intertwined. The human language evolved because it is extremely simple, and yet it conveys so much information. So machines will be talking to machines using human languages, right? Not because they're great languages, but because they're just really, really good at capturing meaning in a very small package, right? So there'll be a lot more of that kind of thing. We'll have individualized agents. They'll be pushed further out to the edge. And then the last thing I guess in this bucket is that these models are going to get smarter and smarter. Now they're again, the models learn from documentation that exists out there in the real world, right? They learn how things work because of documents that exist in the real world. They don't learn things that are not out there documented in the real world. So in the case where let's say companies have pricing is a good example. Many companies have experts who are really good at kind of saying, what should we do with pricing for next season, for the next promotion, for based on this new product launch, right? These are human experts. Their knowledge, the way that they think has never been written down on a piece of paper in a way that's codified in rules that you could feed into a large language model. Instead, the language model is just going to have to absorb all these decisions. It's going to have to absorb thousands of examples of decisions made by humans, and use those to say, oh, we should raise the price, or we should lower the price, or we should change the product name, or we should innovate the packaging, whatever the thing is that the human would have done. So over the next couple of years, you're going to see models that are trained with a lot more depth of that kind of experience, right? So GPT wasn't trained with marketing mix models for every brand in America for the last 30 years. But in a couple of years, you will be able to have a large language model that is trained on that kind of depth of industry-specific information, right? And same with weather forecasts. With you can imagine every other category of large amounts of information that formerly was a human expert sort of grokking it all and becoming the person that relayed it. And now that's going to be these language models. As those training sets get built up and up and up, they'll be able to start making a lot of those decisions or recommendations like the human users previously would do. And what that's going to do is really, again, open up the possibility. It may not be better at analyzing the trajectory of the price of your competitors, but you can apply it to all your competitors every day, which you could never do before, right? You used to be able to do it for one competitor once a week. Now it'll do it for every competitor every day, right? And that's going to, again, change the game in business and make it better for consumers because pricing will be lower, better for the manufacturers because they'll be spending less to get better results. And ultimately there'll be less waste in the system because we'll do a better job of understanding the trends of consumers and weather and shipments and all these different things. So I see enormous amounts of efficiency and profitability and improvement getting built in because language models ultimately just remove the friction of understanding between systems.